In this lesson, we will evaluate some more integrals using trigonometric substitutions. So first, let's review how to decide which substitution to use. If we have a squared minus u squared, the substitution we use is u equals a sine of theta. In this case, du will equal a cosine of theta, d theta. If the integral involves a squared plus u squared, we let u equal a tangent of theta, and then du will equal a secant squared of theta, d theta. If we have u squared minus a squared, the substitution you make is u equal to a secant of theta, in which case du is equal to a secant theta tan theta d theta. Now, find the integral of x over x squared plus 25. So if we are going to use the trig substitution, we have an integral of the form u squared plus a squared. So we are going to let x equal 5 tan theta. Then dx is equal to 5 secant squared theta d theta. So this becomes the integral of 5 tan theta multiplied by 5 secant squared of theta d theta divided by the root of 25 tangent squared of theta plus 25. So that gives us the integral of 25 tan theta multiplied by secant squared of theta divided by 5 times the root. We really have tangent squared plus 1 once we've factored out that 25, and that is equal to secant squared theta. And once that secant squared theta is rooted, we just have a secant theta, which cancels with one of the secant thetas in the numerator. And this gives us 5 times the integral of tan theta secant theta d theta. And an antiderivative of tan theta secant theta is secant, so you have 5 secant of theta plus c. And then, going back to the original substitution, we know that x over 5 equals tangent of theta. So in our triangle, we know that if this is theta, the opposite side is x, the adjacent side is 5, the hypotenuse is x squared plus 25, and secant of theta is hypotenuse over adjacent. So we have 5, the hypotenuse is root x squared plus 25 over adjacent, which is 5, plus c, which just simplifies to root x squared plus 25 plus c. Now just a note, that was not the only way to actually integrate this. An easier method, which is actually totally legitimate to use if you come across problems like this on a test or on your homework, is to actually just do a plain old u substitution and let u equal x squared plus 25. And then du would equal 2x dx. And because there is an x dx in your numerator, this substitution will actually work. You'll end up with 1/2 the integral u to the negative 1/2 du. And that method is actually much, much simpler. So if you see that, if you see problems for which u substitutions work, go ahead and use them. It's just here's how the trig substitution would work if you did it that way. Next, let's find the integral of root 16 minus 4x squared. So here I'm going to think first of all of the 4x squared as 2x, the quantity squared, and I'm going to start by letting 2x equal 4 sine theta. Then 2 dx is equal to 4 cosine of theta d theta, or dx is equal to 4 over 2, or 2 cosine theta d theta. Now we have the integral of root 16 minus 16 sine squared of theta multiplied by 2 cosine of theta d theta. So now we'll factor the 2 out of the integral. Once we factor out the GCF of 16 there, we end up with 4 once it's rooted. So we have 2 times 4. And the integral, this is the root of 1 minus sine squared of theta multiplied by cosine of theta. And 1 minus sine squared is equal to cosine squared. Rooted gives you cosine, so we just have 8 times the integral of cosine squared theta d theta. And now you're going to have to use the half angle identities that allows you to change cosine squared of theta into 1/2, 1 plus cosine of 2 theta. And now we can differentiate. We have 4 theta plus 1/2 sine of 2 theta plus c. And now the slightly tricky bit is that you have sine of twice an angle, whereas your original substitution had sine of just an angle. So you have to change this into being just sine of thetas or cosines of thetas or something. And what you do is you use this double angle identity that says that sine of 2 theta is equal to 2 sine theta cosine theta. There are so many trig identities, so this is one of the ones that will come up in homework. So once I make that substitution, I have 4 theta plus the 1/2 and 2 will just cancel, giving us sine theta multiplied by cosine of theta plus c. And going back to our original substitution, this 2x equals 4 sine theta, well, it's the same thing as saying 2x over 4 equals sine of theta, which really 2x over 4 is the same thing as x over 2, right? Equals sine theta. So in our triangle theta, sine is the opposite over the hypotenuse, so this is x, this is 2, other side is 4 minus x squared. Now, since x over 2 is sine theta, we know that theta is the arcsine of x over 2. So I have 4 times the arcsine x over 2, and sine of theta is x over 2. Cosine of theta is root 4 minus x squared over 2, and then of course plus c. And it's totally up to you, but you can choose to or not to redistribute that 4. And that would give you 4 arcsine x over 2 plus x root 4 minus x squared plus c. Alright, for this one, let's let x equal sine theta. Dx will equal then cosine of theta, d theta. And subbing everything in, I have the integral of root 1 minus sine squared of theta multiplied by cosine theta, d theta, over sine to the 4th of theta. And 1 minus sine squared is cosine squared. Once we root that, we end up with the integral of cosine squared theta over sine to the 4th theta d theta. And now's where it gets a little bit tricky. What you do here is break up that sine to the 4th into 1 over sine squared of theta multiplied by cosine squared theta over sine squared theta. And 1 over sine squared theta is cosecant squared of theta, and cosine over sine is cotangent. square root of theta. And now we're going to do a u substitution, and what you have to remember from Calculus 1 is that the derivative of cotangent is actually negative cosecant squared. So if I let u equal cotangent of theta, du is negative cosecant squared theta, d theta. So this can become negative the integral u squared du, which is negative 1/3 u to the third plus c, or subbing back in my u, negative 1/3 cotangent of theta to the third power plus c. And now what we have to do is change those cotangents back into x's. So the original substitution said that x was equal to sine of theta, so sine theta equals x over 1. So this is my theta. Sine is the opposite over the hypotenuse. The remaining side, the adjacent side, is 1 minus x squared. Cotangent is the reciprocal of tangent, so if tangent is opposite over adjacent, cotangent is adjacent over opposite. So we will have negative 1/3 multiplied by root 1 minus x squared all over x, the quantity cubed, plus c. Another way to express that is this, negative 1/3. The numerator would be 1 minus x squared, the quantity to the 3/2 power. The denominator is just x cubed plus c. So those two answers are equivalent. Either of them is correct. It's just good to know both options. Now next example with e to the x's, let's just start out by making a u substitution so that we don't have to think about it being e to the x and think about it as being u squared. So the first thing to notice is that e to the 2x, if I let u equal e to the x, then u squared is e to the x quantity squared, which is actually e to the 2x. Alright, now if I let u equal e to the x, du is e to the x dx. So this becomes the integral of root 9 minus u squared du. So once we're there, we can let u equal sine of theta, 3 sine theta, and du will equal 3 cosine of theta d theta. So that gives us the integral root 9 minus 9 sine squared of theta multiplied by 3 cosine theta d theta. Now this 3 multiplied by the 3 that comes out once we root makes a 9 times the integral of cosine squared of theta d theta. Once again, we use our half angle identities. We have 9/2 integral 1 plus cosine of 2 theta d theta. And we anti-differentiate, and we'll have 9/2 times theta plus 1/2 sine of 2 theta plus c. And we use the double angle identity on the sine of 2 theta. That tells us sine 2 theta is equal to 2 cosine theta times sine theta. So that red stuff replaces the sine of 2 theta. So finally we have 9/2 times the quantity theta plus cosine theta sine theta plus c. Now let's determine what the cosine theta and sine theta should be. So the original substitution was u equaled 3 sine theta. So we have that sine of theta is equal to u over 3. So in my triangle, this is theta, sine is the opposite over hypotenuse, so my adjacent side is 9 minus u squared. And then theta will equal arc sine of u over 3. So I have 9 over 2 multiplied by arc sine of u over 3 plus, now cosine of theta is going to be root 9 minus u squared all over 3. Sine of theta is just u over 3, of course, plus c. And now let's plug back in what u is and distribute the 9/2. And this gives us 9/2 arc sine of e to the x over 3 plus 1/2 e to the x times the root of 9 minus e to the 2x, of course, plus c. This technique can also be combined with completing the square to evaluate certain kinds of integrals. So first, let's complete the square of x squared plus 6x plus 5. So we have x squared plus 6x plus 5. We have to think, what number do we add here to create something to the second power? And the pattern is you look at half of this number squared. If I add 9, that x squared plus 6x plus 9 component factors into x plus 3, the quantity squared, and you can't just add 9 and not sort of compensate for that somehow. So what you do at the same time is you also take away 9, because effectively then you've added nothing. That's clever, but it's pretty easy to understand once you see it that that's actually true. So x squared plus 6x plus 5 is the same thing as x plus 3, the quantity squared, minus 4. If you were to multiply this out, like take x plus 3 multiplied by itself and then take away 4, you're going to get back x squared plus 6x plus 5. So this changes our original integral into the integral of x over the root of x plus 3, the quantity squared, minus 4 dx. And now that it's in that form, we can use the substitutions that we've used in previous problems to evaluate this integral. So now we make the substitution. We let u equal x plus 3, and then du will equal dx. Also notice that x is equal to u minus 3. So this gives us the integral of u minus 3 over the root of u squared minus 4 du, which we can then break into two integrals. So you have the integral of u over the square root of u squared minus 4 minus 3 times the integral of 1 over root u squared minus 4 du. And now we can use different techniques to evaluate each of these integrals. So on this first integral, I'm going to make just a regular old substitution. So let's pick a new variable. Let's let w equal u squared minus 4. Then dw is 2u du, or 1/2 dw equals u du. So that gives us 1/2 the integral of w to the negative 1/2 dw, which will be 1/2 times 2 w to the positive 1/2, or just square root of w, which is u squared minus 4. The second component we're going to have to use a trigonometric substitution to figure out. So minus 3. Now because our integral here is u squared minus 4, the substitution we will use there will be u equals 2 secant of theta. So du will equal 2 secant theta tan theta d theta. So we have 2 secant theta tan theta d theta over the root of 4 secant squared of theta minus 4. And that gives us, multiplying the 3 by that 2, we'll have negative 6 over 2 secant squared theta minus 1. That's what's going to result when you factor out that 4 and square root it to 2. That's going to equal tangent. So all we have there is the integral of secant of theta. And so we'll have minus 3 ln absolute value secant theta plus tan theta plus c. We can combine the two c's from each individual integration into one new constant. Alright, now we need to change the thetas back into u's and then change the u's back into x's. So remember that we had u was equal to 2 secant of theta. So u over 2 is equal to secant of theta. So in our triangle, if this is my angle, the secant is the hypotenuse over the adjacent. So we have the hypotenuse is u, the adjacent side is 2, the other opposite side is u squared minus 4. So we have root u squared minus 4 minus 3 ln. Okay, secant of theta is just equal to u over 2. So we have u over 2. Tangent of theta will be the opposite over the adjacent. So we have the root u squared minus 4 over 2 plus c. And now back to our original substitution, u was equal to x plus 3. So what we have now is the root x plus 3 quantity squared minus 4 minus 3 ln absolute value x plus 3 over 2 plus the root of x plus 3 squared minus 4 also over 2 plus c. If you care to, you can write these expressions underneath the square roots as the root of x squared plus 6x plus 5. Not required. Another thing to also notice is that much like there was an earlier example in previous notes where we factored out a 1/6, here you can factor out a 1/2 from inside the natural log. So we have the root of x squared plus 6x plus 5 minus 3 times ln of 1/2 multiplied by the x plus 3 plus the root of x squared plus 6x plus 5. And because of properties of logs, this is the same thing as root x squared plus 6x plus 5 minus 3 times ln of 1/2 minus 3 times ln of x plus 3 plus root of all that stuff. And since this constant is arbitrary, and this is also a constant, it can be combined with that constant to make a new constant. So if you're checking your solutions with some other sort of thing, like Wolfram Alpha or a calculator, it might give you this instead. So it's just useful to know that when you're checking your work, you're actually correct. Squared plus 6x plus 5 plus c. So that's not required, you have to simplify it like that, but it's just good to know that that is an actual possibility. Alright, let's complete the square for this particular integral. It's a little bit tricky when your leading coefficient, or the number in front of your x squared is negative. So we have negative x squared plus 2x. First, let's factor out the negative. That makes that x squared minus 2x. And we will add 1. Now because of this negative out in front, that means we've actually added negative 1. So to compensate, we now add positive 1 outside. And that gives us 1 minus the quantity x minus 1 squared. So original integral becomes integral of 1 over the root of 1 minus x minus 1, the quantity squared, dx. And let's make the substitution. U equals x minus 1, so du will just equal dx. So that gives us the integral of 1 over the root 1 minus u squared du. Not so bad. Now we'll do a trig substitution, and we can let u equal sine of theta. So du is cosine theta d theta. And this gives us the integral of cosine theta d theta over the root of 1 minus sine squared theta. And that 1 minus sine squared theta is actually equal to cosine squared theta, which will give us the integral of cosine squared cosine of theta over cosine of theta. And yes, those do cancel. We have the integral of 1 d theta. Yay! The antiderivative of 1 is just theta. So theta plus c. And since we had u equal to sine theta, theta is equal to arcsine of u. So we have arcsine u plus c, and u is equal to x minus 1. So the antiderivative of 1 over the root 2x minus x squared is arcsine of x minus 1 plus c. Next, let's compute a definite integral using trigonometric substitutions. So you have two options. First, you can either choose to antidifferentiate the function and then go back and plug in the numbers at the end once you have your antiderivative. Or you can change your bounds. So you should get the same answer either way, so if you do not like the way that is changing the bounds, you can choose to try it your own way, and as long as you don't do it correctly, you will get the same solution. So I'm going to show you how changing the bounds works, just so you're exposed to that idea. So first of all, the substitution that we'll make here will be x equals 3 tangent of theta. So then dx will equal 3 secant squared theta d theta. And now the bounds. So if x is equal to 0, that tells us that 0 is equal to 3 tangent of theta, and tangent of theta is 0 at theta equals 0. So we're going to have theta equals 0 in this case. And if x is equal to 3, we have 3 is equal to 3 tan theta, as this goes in for the x. 1 equals tan theta, so theta will equal pi quarters. So our integral becomes an integral from 0 to pi quarters. Now x cubed, we take and cube the 3 tangent of theta. That gives us 27 tangent cubed of theta multiplied by dx, which is 3 secant squared of theta d theta over the root of 9 tangent squared theta plus 9. So we have 27, integral from 0 to pi quarters. Now when you factor out the 9 from that root sign, it gets rooted and cancels this 3. And tangent squared plus 1 is secant squared, so that once that secant squared is rooted, it is a singular secant, canceling the other secant, and one of the secants in the numerator. So that leaves us with tangent cubed of theta times secant of theta d theta. And now we use trigonometric integrals to evaluate this particular integral. So we're going to make another substitution. So now when evaluating the integral of tangent cubed secant theta, we have two choices. Either let u equal tangent or let u equal secant. If you let u equal tangent, you need to somehow get a secant squared. We only have secant. So, but if you let u equal secant, the derivative of secant is secant tan. And you see, because the power on tangent is odd, we can take off one tangent and leave it behind to be the du, and we can change the other tangents into secants. So just so we know where we're going to let u equal secant of theta, and then du will equal secant theta, tan theta, d theta. And we're going to have to change the bounds one more time. So here we go. 27, integral from 0 to pi quarters. So tangent cubed of theta will make into tangent squared theta multiplied by tan theta, secant theta, d theta. So that tan theta, secant theta is saved for the du. Now tangent squared of theta, we're going to change into secant squared of theta minus 1. So 0 to pi quarters, secant squared of theta minus 1, tan theta, secant theta, d theta. So we'll have 27, we'll hold off on the bounds for just a second, u squared minus 1 du. Now once you figure out what those bounds are, it's going to be pretty nice. So if we have that theta is equal to 0, u is equal to secant of theta, so secant of 0. And secant of 0 is 1 over cosine of 0, and cosine of 0 is 1, so u is 1. Now, if theta is pi quarters, then u is equal to secant of pi quarters, which is 1 over the root 2 over 2, which is 2 over root 2, which if you rationalize actually just simplifies to plain old root 2. So now all that remains to find the value of the area under the curve that is represented by the definite integral is to evaluate this integral. So the antiderivative of u squared is u cubed, or 1/3 u cubed, minus u, evaluated from 1 to root 2. So that will be 27 times root 2 cubed over 3 minus root 2 minus 27 times 1/3 minus 1. Now, root 2 cubed, you can think about that as being root 2, root 2, root 2, right? So that's the same thing as 2 root 2. So I have 27 times 2 root 2 over 3 minus root 2 is 3 root 2 over 3, common denominator, minus 27 times negative 2/3. So we'll have 27 multiplied by negative root 2 over 3 plus 27 times 2/3 will be 18. And 27 divided by 3 is 9, so my final answer here will be 18 minus 9 root 2. In our final example, we will find the arc length of the graph of f of x equals 1/2 x squared from x equals 0 to x equals 1. And this is just an example of how arc length problems can get really tricky really quickly. So, remember the arc length formula was the length of the curve is equal to the integral from a to b root 1 plus f prime of x, where f prime of x is squared, dx. And pretty nice function here. F prime of x is 1/2 times 2x. And please cancel those 2's, that does just give you x. So the length of my curve is given by the integral from 0 to 1 root 1 plus x squared dx. Doesn't seem so bad. So let's make a substitution. We will let x equal tan theta. So dx will equal secant squared theta d theta. And let's change our bounds. If we have x equals 0, that's the same thing as 0 equaling tangent of theta, which theta is going to have to equal 0 in that case. And if x is equal to 1, that means 1 equals tan theta. Theta equals pi quarters. So I now have the integral from 0 to pi quarters root 1 plus tangent squared theta multiplied by secant squared theta d theta. And 1 plus tangent squared is secant squared. Rooted gives you plain old secant. So I have the integral from 0 to pi quarters of secant cubed theta d theta. Now it turns out that it is actually pretty tricky to differentiate secant cubed theta, so let's do that without bounds on it, just I think it'll be a little bit easier. Alright, so let's find the integral of secant cubed theta d theta. So first notice that secant cubed theta d theta is the same thing as the integral of secant squared theta multiplied by secant of theta d theta. We are going to integrate this by parts using the techniques of one of the earlier sections in this chapter. And for that, I'll let u equal secant of theta, giving me du is secant theta tan theta. dv will equal secant squared theta, giving us v equals tan theta. And that integration by parts formula tells us that we have uv minus integral v du. So uv will be secant theta tan theta minus v du, so minus the integral of secant theta times tangent squared theta d theta. And we will use trigonometric identities to change tangent squared theta back into secant squared theta minus 1. So we have secant theta tan theta minus the integral of secant theta multiplied by secant squared theta minus 1 d theta, or secant theta tan theta minus the integral of secant cubed theta plus the integral of secant of theta d theta. This double negative distributing made that into addition. And now you use the around the world trick. So this is the same as your original. So we add it to both sides, which gives us 2 integrals of secant cubed theta d theta is equal to secant theta tan theta plus the integral of secant theta d theta is ln absolute value secant theta plus tan theta. And now to find the antiderivative we just divide everything by 2. So the antiderivative of secant cubed theta d theta is 1/2 secant theta tan theta plus ln absolute value secant theta plus tan theta. That's a pretty tricky integral. Now back to the original problem. We're trying to find the length of the curve, which was given by the integral from 0 to pi quarters of secant cubed theta d theta, and we found that the antiderivative of secant cubed theta was 1/2 secant theta tan theta plus ln absolute value secant theta plus tan theta. And we're going to evaluate that from 0 to pi quarters. So first, plugging in pi quarters, we'll have 1 over root 2 over 2. Tangent of pi quarters is 1 plus ln absolute value 1 over root 2 over 2 plus 1 minus 1/2. Secant of 0 is 1, tangent of 0 is 0, plus ln absolute value 1 plus 0. So that. Now, as we discussed earlier, 1 over root 2 over 2 is actually equal to root 2, so we have 1/2 times root 2 plus ln of the quantity root 2 plus 1 minus the second term is just 0. So the length of this curve is given by 1/2 times the quantity root 2 plus ln of root 2 plus 1. And as you can see, finding arc length often results in antidifferentiation of functions which are not very easy to antidifferentiate. I mean, all you were asked to do is find the length of an arc of a pretty simple parabola between two pretty simple numbers, and look at how awful it was. So you can see why. I mean, arc length is often the case. If you're finding arc length, you have to use some kind of approximation techniques to evaluate or get an estimate of that integral, sort of like a left sum or a right sum or trapezoid rule or Simpson's rule.